Thank you for taking the time for my session. It's about Google Cloud Datalab. It's a Jupyter running on Google Cloud, and I'll be talking about how you can combine BigQuery and TensorFlow by using the Datalab as a hub of those tools. I'm Kaz. I'm a developer advocate for Google Cloud, especially focusing on the data and analytics products like a BigQuery or TensorFlow. I have been working at Google for over 6.5 years. And for the last 3 years, I have been working as a developer advocate. So what is Cloud Datalab? How many people actually tried Datalab? Oh, like over 10 people, thank you. It's a Jupyter notebook running on Google Cloud. So it works as a Jupyter notebooks, but it also provides the APIs to access the Google Cloud services, such as the Datalab, which is a MapReduce-like batch processing system plus stream processing. Compute Engine is the virtual machine. Cloud ML Engine is a runtime for TensorFlow. Cloud Storage. BigQuery is a data warehouse. Stackdriver is monitoring tool. So you can access those cloud tools as well as the usual tools such as TensorFlow, NumPy, and Scikit-learn, Matplotlib, all combined on the single Jupyter notebook environment on Cloud Datalab. And so it's easy to get started. So you can just go to the cloud.google.com/datalab, where you have all the materials to get started. First, you have to install the Google Cloud SDK on your laptop, and then execute the Datalab create command. That will create a Datalab instance on cloud. Actually, that is a virtual machine. Google Compute Engine virtual machine is running on cloud. And then the cloud Datalab command will establish a SSH connection between the virtual machine and your laptop so that you can open your browser and access to the localhost 8080 to open the notebooks within your laptop. But your instance is running on cloud. It's so easy. It provides all the APIs to access the Google Cloud services like a BigQuery or machine learning engine. And also it provides the Git support. So you can, when you have updated your notebook, you can push it to the Git repository within the Datalab environment. Also, it is integrated with Google Chart. So not only using the popular tools such as Matplotlib or Plotly, you can also use the Google Chart APIs as well. And recently, we announced the latest version of the Cloud Datalab. It includes the support for the Python 3 and the auto-idle shutdown feature, because Datalab is running on the Google Compute Engine instance on cloud. If you leave it running, then you'll be charged for the virtual machines. So now it supports to be shut down automatically so that you don't have to worry about the charges. And also it supports the TensorFlow 1.2 and Beam 2.0. And the latest release also includes the preview version of the so-called ML Workbench, which is an easy tool for going through all the machine learning life cycles, like starting from the ETL and pre-processing all the data, or the training your model, validating your model and deployment. And we are trying to provide a workbench or toolkit that can support and integrate all the tools available on the Google Cloud and make it easy to build a pipeline for you. But it's still preview, so maybe later in this year, we'll be providing more and more proper documents or samples for the ML Workbench. So today I'd like to talk about how you can use the Cloud Datalab to integrate two important cloud services from us. That is Google BigQuery Data Warehouse and TensorFlow, which is the machine learning framework. Let me start with BigQuery. What is BigQuery? BigQuery is a data warehouse service from Google Cloud. And that is based on the very simple experiment we have done at Google many years ago. We have done an experiment to learn how many disk drives you would need to scan all the 1 terabyte of data stored on hard disk drives, scanned in 1 second. If you stored 1 terabyte of data in a single disk drive, you can imagine that you would take like several hours to read through all the data. But if you split the data into like 100 drives or 1,000 drives, it can get much, much faster. So how many disk drives you would need to scan all the 1 terabyte in 1 second? The result was 5,000 to 10,000 disk drives. So there was a very simple idea. Why not building such a massively parallel data warehouse by using the thousands of disk drives and CPU processors in Google Cloud? So that's the BigQuery. Because we have the data center as a computer, that means we have the tens of thousands of servers in a single data center, as a whole data centers. And each server in a data center is working as a node in a massively parallel computing resource. And to implement that, we have been building a very unique technologies. Two technologies. One is the container technology called Borg. Borg is our own proprietary container technologies. It's just like a Docker, but the largest difference is the scale. Because with a single cell or single cluster of Borg, we manage 10,000 machines, physical machines. So any software engineers at Google can execute single Borg command to run her or his application or process on hundreds of machines in a few seconds. So that's the large scale container technology we have at Google. And the second technology is the network. We have been building our own hardware for switch fabric. We are not using the commodity routers or switches such as Cisco or Juniper for building our data center network. Instead, we have been hiring the hardware designers for switch fabrics and building the network fabric from scratch that can host 100,000 ports of 10 gig or 40 gigabit Ethernet. That is 1.2 petabit per second. So combining two different technologies, the container technology and the large-scale network, you can build the very large, massively parallel processing data warehouse. That is the BigQuery. So every single SQL you'll be running on BigQuery will be processed by 1,000 to 2,000 CPU cores with hundreds of disk drives running in parallel. So it's totally different architecture compared with the other competitors' data warehouse system. So let's take a look at the live demonstration of how BigQuery can work with Cloud Datalab. So this is the screen of the Cloud Datalab. It's just a Jupyter notebook, but as you can see, you can directly write the SQL running on BigQuery within Jupyter notebook. So this is a sample query called wiki10b, where we are accessing a sample table named wiki10b that has the 10 billion rows of the page view data imported from the Wikipedia service. And now I'm trying to count the page views and aggregating by the titles of each Wikipedia page. And now I'm using the regular expression matching, specifying cloud as a keyword or text pattern, and order by the titles. So usually if you run this kind of the query with regular expression matching, there's no way to build the database index or caching. So this query will be processed as the full scan or table scan. You have to read all the data from the hard disk drive or SSD and process all the regular expression matching with CPUs. So usually if you do this kind of the query on the other kind of the data warehouse or database like MySQL or other products, your database administrator will be so mad at you. They will not allow you to this kind of this stupid query. But with BigQuery, you can easily execute it. And now I have defined a query called wiki10b. And because Datalab provides the Python API, to run the BigQuery query within the Jupyter notebook, you can easily execute the defined query from the Python code like this. So now it's running the query on BigQuery instances on Google Cloud. So this is not a cached result. So this is actually processed all the data stored on the hard disk drive, hundreds of hard disk drives, processed by the thousands of CPU cores. They got the result, the real-time result within like 5 seconds or 5 or 6 seconds. This query read about 400 gigabytes of data read from disk drives, not caching or not using any index. So this is the performance of the Google BigQuery, and everything is accessible through the Cloud Datalab. So BigQuery is fully managed, no ops data warehouse, and you can process the terabytes of data in tens of seconds. But still, the cost is so low, inexpensive, compared with the competitors' products. And it's so easy to use. It's just on standard SQL. So, and also it's scalable, so that means any slow-running query or homebrew queries or quick and dirty queries does not affect the performance of the production queries. So that's the reason why many BigQuery users are letting anybody in the enterprise, like salespeople or marketing people or executives, running their own homebrew copy and pasted SQLs directly on the production instance of BigQuery. Because it's scalable, nobody would be affected by the slow-running queries. So that was just a very, very basic demonstration of BigQuery and Datalab. And what about the more smart analytics by using feature vectors? So I'd like to talk about how you can combine the data warehouse BigQuery with machine learning, learning with TensorFlow and grand machine learnings. And Datalab will be a hub for integrating two technologies. So let me show some interesting example demonstration first. This is a demonstration called Query Smart, where you can choose 3 different kinds of queries. I will be running a document similarity search as a sample. This is a sample query of Query Smart that will be searching for a similar document, a document similar to a specified document. And on BigQuery, we have a public data set for many different kinds of the data. And this sample is using Stack Overflow questions for 10 million documents, 10 million questions. So if you specify one of these key questions, like converting string into Java, then BigQuery is running a query against 10 million documents or questions to compare the 2 different documents are similar or not. This is not based on any cached or indexed search or tag or labeled-based search. Instead, it is actually comparing 2 different documents for 10 million documents in real time. And usually, the query would finish within 30 seconds. Let's wait. Yeah. So almost 30. Okay. So as you can see, the next question is the key document, key question. And this is the list of all the results you got, the similar questions on Stack Driver. So as you can see, these are all similar questions. And this is not based on the label or the tag-based search. So how do you implement this? How do you find similar posts on Stack Overflow? These are what I have done with these demonstrations. At first, you have to split each sentence into words, the segmentation. And then you extract the feature vectors from each post, each document. And this is the key technology in BigQuery, that is user-defined function, or UDF, that allows you to define a small JavaScript code running inside your SQL. So that allows you to do very simple pre-processing or small calculations within the SQL. So in this case, I've used UDF to do a similarity calculation between 2 feature vectors. And then you can use the user-defined function in any SQL you'll be running on BigQuery. So what is feature vector and what is the benefit of using feature vectors? If you're using the ordinary SQL-based relational database, you will be using simple tag or labels to find content. Like if you are trying to find the content with talking about movie or music or actor, you'll be putting tags or labels like a movie or music tag. But instead of using those labels, you can use your feature vectors with a bunch of the numbers in a vector. Each number represents the how much topic, how much the frequency of the words or topics reported in a single document. So this particular document with this vector is talking about movie a little and does not talking about music so much, but talking about actor so much. So you can represent the content by using the feature vector. And you can extract the feature vector from those Stack Overflow questions by using the simple algorithms. In this case, I have used TF-IDF. This is a classic, very simple way of extracting feature vector from documents. This is not a machine learning stuff. It's just trying to calculate the frequency of the important words such as Java or CSS or text selections. And TF-IDF allows you to remove all the trivial words such as if or there or a or you, and you can extract the most important words on these frequencies. Then you can compare the similarities between two vectors by using the cosine similarity. And if you do the same thing with words, you can have the vectors like this. If you have a vector for music, word music, then the vectors for songs or dances or artists will have the high similarity to the music, the vector for music. So you can do the same thing with your document. And to do that, usually many people are using the bigger things like Apache Hadoop MapReduce cluster or Apache Spark, waiting for tens of minutes, processing all the terabytes of data. But instead, by using BigQuery, you can just use a user-defined function to do the calculating the TF-IDF-based similarity search like this. Because, as I mentioned, BigQuery will be running on 1,000 to 2,000 GPU cores. The JavaScript code you'll be running with UDF will also be running with the 1,000 or 2,000 GPU cores. That is the one with the largest scale information processing system you can access. And everything can be finished within tens of seconds, not tens of minutes. So let me actually show the demonstration how I have implemented the document similarity search by using Cloud Datalab. So again, you can directly write down your SQL inside Datalab and execute it. So this is the simple SQL to look at what kind of the content you have on the BigQuery other stack driver questions. So the table has the title and body columns where it has the title and the body of each question. And then you can write a simple user-defined function for doing the segmentation, splitting the sentence into words. It uses the simple JavaScript-based regular expression matching to remove HTML tags, converting everything into lowercase and extracting the words. So you don't have to prepare your Hadoop cluster to doing this kind of the trivial, simple conversion or formatting. So you have the words separated, the sentences split into the words. And then you can extract the feature vectors by using TF-IDF, by using user-defined function. TF-IDF is very simple algorithms. It's not a machine learning. It's just counting numbers or frequency of each words in a document. But again, in past, it's really hard to process this kind of the logics within data warehouse. So many people has been using Hadoop or Spark. But with BigQuery, you can run your own logic on BigQuery so that you can easily get this kind of the feature vectors within tens of seconds, like 20 or 30 seconds. So it's ready to execute the similarity search. So we define the user-defined function for calculating similarity between two vectors. It's just a simple calculations, multiplication and additions between numbers. And then you can use your own user-defined function in any SQL you'll be running. So now it is running. So even if you have 10 million posts, the all processing should be done within like 16 or 20 seconds. It's so fast. So you're seeing the result from the BigQuery where you have all the similar questions on Stack Overflow talking about deleting or adding a column to Microsoft SQL Server. So far I haven't talked anything about machine learning. I have used a very simple TF-IDF algorithm. So let's try using machine learning to execute more smarter analytics. How to analyze data with much complex features. If you are using the standard SQL, simple SQL, it's very hard to capture those complex data structures, especially when you are handling the unstructured data, images or audio, or user data with the hundreds of the attributes or the dimensions. It's really hard to build your own SQL to look at the tens of different attributes or dimensions in a single query. So in that case, it's really easier to use machine learning or neural network. Because by using neural network, it can try to extract the features by looking at the past data and training data. So this is a demonstration called TensorFlow Playground, where it tries to capture the double spiral patterns inside the training data. So initially, computer doesn't make any sense on the data, but if you keep providing the training data and providing the computing power, the computer tries to capture a certain complex patterns or features from the data. And this is something you cannot do with the SQL or standard data warehouse. So how about combining these two technologies? And at Google Cloud Service platform, we provide a bunch of different machine learning services. And there are two kinds of the products. One is the pre-trained ML model at the right side. These are all the APIs, simple APIs with pre-trained model inside it. So you don't have to have any expertise on machine learning, and you don't have to train your own machine learning model. Instead, you can just send images, audio, or natural language text to the API, and you'll be getting the result, such as the labels, cat or dog, or the wedding party from APIs. It's so easy to use. But in this session, I'd like to focus on the custom ML models. To use custom ML models, we provide the products such as TensorFlow, which is an open source tool for building your own machine learning model, and the machine learning engine or ML engine. This is a commercial service for running fully managed TensorFlow runtime with the tens of the CPUs or GPUs. So as you may know, TensorFlow is the most popular deep learning framework in the world. Inside Google, we're actually using TensorFlow for building almost all new machine learning or AI-based services. And it's also getting popularity in the community because it's so easy to use. You can just write tens of Python code to define your neural network model and let TensorFlow optimizing your neural network model with the different algorithms such as the gradient descent. And what is machine learning engine and what's the difference between TensorFlow and ML engine? The ML engine is a commercial service that provides the fully managed TensorFlow platform or runtime on Google Cloud. So if you're using open source TensorFlow, you have to take care of the runtime platform by yourself. Like, you have to prepare the virtual machine instance, and if you want to use GPU, you have to install CUDA driver, or cuDNN, and you have to be careful about the versions of those library. And if you want to have the distributed training environment, you have to build your own Kubernetes cluster You have to think about how to split your workload into multiple devices. But by using the machine learning engine, you can forget everything about those things. All you have to do is build your own TensorFlow model and prepare training data and upload them to the ML engine, so that the ML engine take care of building and operating your distributed training systems based on TensorFlow. And also it provides the hyperparameter tuning automation called HyperTune. It uses a Gaussian process to minimize the number of the trials with the hyperparameter tuning. And here I'd like to show two different use cases for combining BigQuery with machine learning engine or TensorFlow. The first use case is the most popular one, using BigQuery for preprocessing or ETL. So extracting the data from BigQuery, and then you can going through all the life cycle of the machine learning. So let me show some demonstration. I have prepared a demonstration called classifying Manhattan with BigQuery. This is a very simple sample code running on Cloud Datalab to train a very simple neural network model that can classify location, geolocation is in a Manhattan or not. So at first, let me execute a BigQuery SQL that extracts the training data from BigQuery public dataset. Here, I'd like to use a public dataset called NYPD collisions. That is a public dataset which has all the accident records in New York City. So every time you have a car accident in New York City, it is imported into BigQuery as a public dataset. So let me execute. So it's running the query. So this is the data. So each accident has the timestamp and latitude and longitude pair and borrow. So we'll be using this data to train the neural network model that can classify whether a single geolocation is inside Manhattan or not. But there's some useless data like these data which doesn't have any borrow. So we'd like to do some simple pre-processing. So with BigQuery, you can write a very simple SQL to exclude those data without any latitude and longitude. And also, I want to shuffle the all data and want to extract top first 10,000 rows. So let me execute. So I have just defined this SQL called NYC collisions. And again, you can use the BigQuery API inside Datalab to execute the query, define the query, and you can convert it to the pandas data frame. And I'll be converting the data frame into the NumPy array directory. So, and the result is that you will be having the result converted into a NumPy array. Let me execute it. So by using the BigQuery API on Datalab, it's so easy to do the pre-processing with user-defined function and standard SQL import, and the result will be imported as NumPy array or pandas data frame, like this. We have the pairs of the latitude and longitude for 10,000 rows, and each pair has a label, whether it's in Manhattan or not. And because it's just a Jupyter notebook, you can access the usual tools such as the scikit-learn or matplotlib for standardization or plotting, like this. So you can see the shape of the Manhattan. You can even see the Central Park is in the middle. Let's split the data into training data and test data. And this is where you are using the TensorFlow for defining a deep neural network model. You can import TensorFlow. And now TensorFlow has so-called high-level API compared with the traditional low-level API. So it's getting much easier to define a deep neural network model by using TensorFlow. Or you have to write to define a simple neural network is writing like 4 lines of code here. It's a deep neural network classifier API that defines 4 hidden layers, and each hidden layer has 20 nodes or neurons. So I have defined a neural network. And let's take a look at before training, let's take a look at, let's visualize how the network model is stupid before training. Every machine learning algorithm is stupid like this. So because the neural network is initialized with the random numbers, it thinks this part is Manhattan. This is not correct. So we have to train the model. So by calling the fit method of the DNA classifier object, you can train the model by passing the training data extracted from BigQuery. So it's just like the scikit-learn. The only difference is the scalability. So as long as you're using this high-level API, it can be scaled out into tens of the GPUs and terabytes of data. So you're seeing that that model is gradually getting smarter and smarter by training. And we got the final result. So it's pretty smarter than the older one. The accuracy is 99.95%. So you have seen that it's so easy to integrate two different things, BigQuery data warehouse for extracting the training data and do pre-processing, and define your TensorFlow model by writing a few lines of Python code. So let's take a look at the use case number 2, which is using machine learning model to extract feature vector search on BigQuery. So let me go back to the Query Smart demonstration. So on Query Smart demonstration, there's another sample called image similarity search, where you can choose one of the key, which one is better? Yeah, key images. So now it is running a BigQuery SQL query against 1 million images. Actually, image itself, the image files are on Google Cloud Storage, but BigQuery has the URL for those images and feature vectors of 1 million images, so that BigQuery can compare whether a single image is similar to another image. And again, this is not based on the tagged or label-based search. It was actually comparing the colors and shapes and patterns, textures of two different images. It is just not looking for sunflower. Let me try another query. So how about this? So this query is not looking for a picture. It is looking for images that has similar texture or patterns or shapes. And usually you have to build your own Hadoop MapReduce cluster or Spark cluster to do this, and you have to wait for tens of minutes or many hours to finish the batch processing. But with BigQuery, you can get the result within 30 seconds, like a 20. Is it frozen? I think it's frozen. Maybe my browser is having a problem. Let me try with other. How about this? It's not looking for Dragonfly. So you'll be seeing images with green background and some insect-like patterns in front of those green backgrounds. And I hope that query would finish within like 20 seconds. Not sure. Oh, we got the result. So as you can see, many of the images has the green background and patterns like a Dragonfly, but it's not looking for Dragonfly. Okay. So what I have done to build this demonstration is to, at first you have to import all the images on Google Cloud Storage, 1 million images. And then I have executed a batch processing with machine learning engine with TensorFlow model that applies the CNN model to the images to extract feature vectors, not labels. And then import the feature vectors to BigQuery and use the UDF to calculate the similarity between the images. So usually if you are using CNN model, many people are using labels such as dog or cat. But by taking a look at the numbers the vectors in the final layers, you can extract the feature vectors. There's about 1,000 numbers in the final layers of the VGG16 model, and each is the feature vectors, and each elements or numbers in the feature vectors represents the features such as the patterns or colors or context or shapes in images. And by using TensorFlow, it's easy to extract those feature vectors by specifying the layer position of layer. And then again, you can compare the distance between the feature vectors by using user-defined function. So it's a very simple mathematics. You can define with UDF to calculate the similarity. So that you can use the user-defined function distance at any queries you'll be running on BigQuery. And you can even let the salespeople or marketing people or executives using your user-defined functions to run their own homebrew SQLs. And I have used the document search and image search as examples, but this technique can be applied to any other use cases where you can define feature vectors against any content. For example, if you have a bunch of products, if you can define a feature vector for product, you can easily get the product recommendation engine just by using BigQuery and TensorFlow. You can find the similar users like premium users or cheating users by defining the feature vectors, or you can find the similar IoT devices by looking at the sensor data or music or any unstructured data. So, summary, so Datalab is a one-stop shopping for all the cloud-based data analytics. It combines the Jupyter notebook with the cloud services. And BigQuery, as you have seen, it's a fully managed petabyte-scale data warehouse. Single query can run on the 1,000 or 2,000 CPU cores with hundreds of disk drives. And user-defined function is the most powerful feature of BigQuery that can replace many parts of the existing Apache Hadoop MapReduce or Apache Spark workloads. And you can combine the user-defined function with TensorFlow to extract the intelligence. And Datalab is the hub for all the powerful tools I have explained. So that's it. Thank you so much.